Hello everyone, welcome to this TA class or tutorial of the course Microsensor Implantable Devices and Rodent Surgeries for Biomedical Application. In today's TA session or tutorial session, we will be looking at some of the basic examples focusing on lithography. Now as you all know, lithography is one of the important process in the entire microfabrication sub-process, and as the course focuses on implantable devices and rodent surgeries for biomedical applications using microsensors. So, most of our focus would be on microstructure devices, microelectrode arrays, or some additional MEMS based structure which can use in drawing more neural inferences out of the obtained data or using data obtained using sensors. In the previous some of the other classes I have explained about neural signal processing, that once we get the data, how to make sense out of it. In this class we will be going a little bit in the experimental flow, we will be going little the preliminary or earlier stage when we are fabricating particular microelectrode array. Then we will be depositing some of the materials, then we will be patterning it, we will be etching it. So, depositing is an additive process. How do we do that? So, Professor Hardik would have already covered that we will be using PVDs, CVDs. PVD includes thermal evaporation, E-beam evaporation, sputtering. There are subtypes of that. In which particular process flow, what kind of thin film deposition should be used, that needs to be known, right. Then further if you go, then for lithography also there are several approaches. There are contact based, then there are projection based, some additional lithography. Some lithography depends on different principles of optics, some depends on diffraction limited lithography, some are reflection based lithography. Based on your process flow, your final design, your structure and application, you can opt for a particular sub process of the process. Additionally, when there is etching, there is a wet etching, dry etching, etc., right. So, these are like some of the basic steps for microfabrication. Of course, it gets evaluated by characterization, we will come to that, but in that entire microfabrication process, today there is one important thing is lithography. Now, why that is important? So, the aim of microfabrication or nanofabrication process is to develop the desired structure having micrometer or nanometer dimensions. So, the thing is that final smallest dimension which you can present or which you can put it or pattern it on your substrate is known as resolution. So, for any microstructures, resolution is very important parameter which is directly dependent on your process of lithography. So, this is like a conceptual or fundamental importance of lithography in microfabrication process. One additional thing is lithography cost almost half of your overall microfabrication cost. So, lithography does not only have a conceptual importance, but it also affects your particular company or foundry when it comes to financial aspects as well. You might have you can search if based on your interest that how many recalls happened for a particular foundries or electronics industries. It is very costly, and one recall can cause a collapse of a complete microelectronics company. Okay. So, like important process, very vital when it comes to developing your microelectrode array, especially for neural engineering projects and all. Today we will be seeing some of the basic sub process of that, numerical based on that basic sub process which is already process is covered. We will see the numerical in this class, and also we will see how we can approach. The another agenda of the class is the numericals, means it is a very generally a mathematical form of your concept which you have understood. Here what we will see is not only the mathematical aspect of that, how it is connected or what is the physical interpretation when it comes to a lithography process or overall microfabrication process, and also we will see how we can further go one step ahead to meet whatever the current standard or state of the art technology. So, that is the overall agenda, to induce that particular thrust in you to identify that okay, how current state of the art lithography techniques would have reached to a particular dimension, particular feature size. So, let us start the session. If you can see my screen, we will see the first numerical. So, the problem statement says a photoresist gives a final thickness of 320 nanometer when spun at 2800 rpm. What spin speed should be used if 280 nanometer coating of this same resist is desired? Okay. So, first point is this depends on the spin coating subprocess of the photolithography, right. So, this is overall process flow of the photolithography. It starts with here wafer. Now, wafer means not only the procurement of wafer. Before using the wafer for any subprocess, we do cleaning. Okay. It needs to be cleaned. Cleaning, there can be RCA cleaning. There are two steps of RCA cleaning. You can explore it at your interest and pace and convenience. Third thing is after RCA cleaning, there is something called pre-rana cleaning, right. So, different process for different application. You can use different form of cleaning. Once the wafer is clean, you can purge nitrogen to make sure that all the moist and all will be residual moist, something is there based on post cleaning will be removed. Once the wafer is cleaned, this is your first step. Once the wafer is clean, you have to coat the photoresist, right. So, the important factor here is the thickness of photoresist. For each photoresist, if you see the data sheet of each photoresist, you will find a graph with spin speed, right, and final thickness. Okay. So, this graph would be available for each photoresist data sheet, and it is a common sense. If you think that your wafer is there on which you will apply or pour the photoresist, which is like a liquid with a predefined viscosity. So, when you spin it, the higher the spin speed, the final thickness would be less. If you spin it with a very low speed, then you will get a much higher thickness. That photoresist bulb or that photoresist semi liquid which is applied on your wafer will have a very like high or more thickness if it is not spun at high speed. So, more or less it will be like this kind of graph. Okay. Now, for each particular photoresist, this graph, this equation or relation between your spin speed, right. So, let me tell it omega and your thickness. So, let me say it is d. Okay. So, distance between omega and d, there will be some functions, right. So, this is known for a particular photoresist for a finite range of spin speed. Okay. And based on your subsequent steps, which is the first one is this is third step is pre-bake. Okay. Now, again pre-bake corresponds to three things. Also, coating depends on not only this, for how much time you are coating it. Okay. So, in this case we are considering the same resist and same process. So, we will consider the same amount of time is being provided. There is a different relationship with respect to time as well, but for now we will consider spin speed and thickness. For pre-bake, I was telling that this thickness is dependent on several subsequent steps of the entire lithography chain. For pre-bake, the temperature of like baking, the time for baking, okay, both are decided. Same goes for PEB, temperature and time. Now, this PEB is post exposure bake. Exposure is the key step in any lithography process, which is this, starts from illumination, goes through this condenser lens through some strategy known as stepping and scanning, some and mask. This is our main input, okay, main input or design which you want to finally pattern onto your wafer. So, this is your key input mask, and then condenser lens I have already mentioned, condenser lens, then this is mask, then objective lens, finally some known optical sequential events happen and you will be able to get your desired pattern from mask to your wafer. So, this is key step is this optics. So, this is again very important key step. After exposure you will be having a post exposure bake. Pre-bake and post bake, both temperature and time for a particular photoresist, which is the optimal time of that, it is identified. It can be 100 centigrade for 1 minute, 110 centigrade for 1 minute to remove the additional some residues and all this thing. So, and further it should be ready for development. So, when you expose it, your UV rays or light from this illumination part, there are different sources, there can be excimer lasers, other sources and all. So, that will fall onto your mask will have a certain pattern. So, light will get diffracted and it will pass through some portion and get diffracted at edges, and then based on this objective lens and diffraction and several other optical known series of events, you will get it here. But when you get it here, that particular portion of your wafer will get will have changed the that particular portion where PR is there will slightly have a different chemical property and which behave differently during development. So, basically in a simple word, if I say, what exposure does is it maps your mask design in terms of different chemical region on your wafer, which you can further use when you develop it. Your final desired thing will get etched either or will stay there, other part will get removed based on which kind of photoresist you are using. So, in lectures professor would have already covered positive and negative photoresist, right. So, based on that, a particular portion on your wafer will stay, other portion will get etched off and you will get your device. Okay. So, this is like an overall quick recap of the explained lithography process. So, just to brush up the things what have been covered and give you a kind of a feel of this particular what exactly to make you understand what exactly this particular problem statement suggests. So, now let us move go ahead with the example. So, this example is related to the coating step, which is this step, okay, from the entire lithography process. Now, we will focus on coating step. Okay. So, let us see as I mentioned the relationship between spin speed and your thickness is already known for a particular resist. So, it is given that resist thickness is inversely proportional to the square root of spin speed. So, nothing but resist thickness, I told you D is inversely proportional to the square root of spin speed, right. So, we have we can feel that higher the spin speed then lower the thickness, lesser the spin speed higher the thickness, but how much higher or how much lower, how can we identify the relation. So, this is the relation between them. Now, D1 D2 is like two different thickness at two different situations, omega 2 and omega 1 are the final spin speeds. So, if you just quickly see the values given to you, you have been given here one particular thickness and one case where thickness and spin speed is given, one another desired thickness is given, all we have to find is the final spin speed. So, this equation contains 4 variable, 3 of them are known. So, finding fourth one would be a very easy peasy, right. So, just if you put the value you will get this particular value. Again here the catch is not just use the equation and put up the value and get the value. You should also understand what it wanted to convey. When thickness was 320, you have to spin it at 2800 rpm. But when the thickness you want to even lesser thickness, now how much lesser or how much more you want depends on your subsequent processes, it depends on your chemistry for development and etc., several other parameters. But when you want a lesser thickness, how much you should increase your spin speed. So, that is just to understand that particular aspect, that when it was at 320 nanometer 2800 rpm, when you go to 280 nanometer you have to increase it. How much? You should at least increase it by almost 20 or more than 25% something. So, you can quantify it based on this particular relationship. The lesser if you want to go, you can go, but then again as I mentioned, it depends on subsequent optical photochemistry and what you are getting and all. Once everything is done, you can check your finally desired generated device using this metrology. Metrology is nothing but also known as characterization. Okay, very important. So, there are several process for characterization. Some of them are like SEM, imaging technique, TEM, then you can do some other spectroscopy and FTIR, XRD, UV vis. Based on different structures and different process flows, you can use different characterization technique to evaluate whether you have got the correct desired pattern or not. These all patterns are of micrometers and nanometer dimension. Also, when you are making some chemicals and playing with those kind of thing, you should know that a particular bond exists in that chemical or not. All this thing can be identified using this characterization technique. It is like an evaluation parameter. Okay, in normal words you can say for validation and etc. So, this is like a first example of a sub process which focused on coating. So, now let us see another example which is focused on one other sub process of the chain, lithography chain, is this I would say this complete exposure. Okay, because another why I am more focusing on this particular thing is, again, for fabrication lithography is the heart of fabrication. Okay, entire final pattern etc. depends on lithography. But if I talk about lithography, optics and subsequent exposure, illumination optics includes illumination, exposure, everything. Okay, this exposure happens for very less period of time. It can be few seconds, but does the trick, does the job. Sometimes even it should be very precise as well. When I talk about precise exposure or precise optics in lithography, this if I say, I have already written earlier that it is a condenser lens, right. When I say lens here, objective lens, there will be so many giant lenses which has been precisely placed exactly at that particular position. Even if it is 1 millimeter here and there, you might not get your desired pattern as an final output. So, very critical. Entire fabrication depends on lithography, lithography depends on your particular optics step. So, that is why the subsequent numericals will be focusing little bit on one of the very key aspect in a simplistic manner for that particular exposure step. So, let us move ahead. This is the problem statement for the second problem. What is the ratio of minimum feature sizes achieved using G line and I line wavelength of a mercury arc lamp? Okay. Now, first question should be what is G line, what is H line? We will come to that, and consider that the same lithography system is used. Okay. So, this is basically emission spectra of you can see there are different form of wavelength and different type of illuminations are provided here, and we have been provided that there is wavelength of mercury arc lamp. So, these are like range for mercury arc lamp. Okay. Now, there is a relationship between the wavelength and resolution. Okay. So, wavelength and resolution, there is a relationship. Resolution is nothing but minimum feature size achieved. Okay. There is something called minimum half pitch which you can successfully reproduce on your substrate. So, that is known as your resolution. It depends on several things. it depends on numerical aperture. Numerical aperture is the ability of the lens to acquire a certain particular portion of the light. It depends on some process parameter. It depends on at which particular angle you are illuminating your mask and how the light has been guided from your illumination to mask and from mask to your wafer. So, when you talk about illumination device to your mask, then condenser lens will come into the picture, and when you talk about mask to your wafer, at that particular time your objective lens comes into the picture. And when I say objective, again, when lens, objective or condenser lens, there are series of lens strategically placed in a particular precise location. So, here in this particular case we have been provided that there are two types of sources have been used, one is G line, one is H line. Okay. So, what you got, what you information you will get from this is you have been given two particular wavelength. One of them is lambda G, which is nothing but 436 nanometer, other one is lambda H, which is nothing but 405 nanometer. Now, why I have taken these two values, then studies and all have been already done, that at what wavelength this emission spectra peaks. What do I mean by peaks? Means you will get a photon or you will get a particle with highest locally highest, and you have in mathematics you learn local maxima, local minima, etc., right. So, these values will give you the photons with higher energy, so that can with less period of time or optimally you can get the job done. When I say get the job done, it is about lithography, right. So, let us see how to approach this particular problem. So, yes, this is very important, it is a very simple equation shown here, but very important and have a huge importance when it comes to resolution. So, as I mentioned, resolution depends on your wavelength, it depends on your numerical aperture, it depends on some process parameter which is K. So, and again when I say resolution, ideally how much resolution I want, I should get as smaller resolution as possible. Why that is important? Because when you have a smaller resolution, which means you will be having you can have in the same device you can have more functionality, or you can have for the same functionality smaller and smaller device. Just a simple, before 10-15 years you see your computers or desktop, you require it would like a bulky equipment or like that, whereas now most of your work which you can do in your laptop or computer you can do using your mobile phones. So, how it is possible? That is due to evolution or able to incorporate more and more logic on your same chip, and that is where resolution comes into the picture. So, when I say to improve the resolution here, which means we are going in terms of resolution, we are going as smaller as possible, and that is the desired need. Okay. So, how do we improve the resolution? If you do not know anything about lithography, if you do not know anything about optics or this microfabrication, still you can say that in this case that if K is less I can improve, if lambda is less I can improve, if numerical aperture is higher I can improve. So, how do we do that? So, these are known techniques to improve the resolution, they are known as RETs, resolution enhancement techniques. Why I am saying all this thing? Because these things are important when you talk about all this minimum feature size, G line, I line and all. Based on your interest, I would encourage you to go and check all these RETs. Okay. So, let us again focus on the solution of this particular problem. So, equation is given. Now, you additionally know what are the RETs as well. I would encourage you to go into the detail of all four of them. Lowering wavelength depends on this particular parameter, fourth one depends on this. Phase shifting mask, for now we can say it is related to this also, first one, right, it is related to and it is related to this as well. Then it comes immersion, immersion will heavily increase your NA, so third one will come here, and off axis illumination will definitely reduce your K. So, each technique affects your formula or one of the parameters accordingly. So, now you see that minimum feature size and all is given. Additionally, it is given that same photolithography system is used. So, for same photolithography system, your K remains constant. Okay, K remains constant. Also, when same photolithography system is used, means lens and all arrangement will remain same. So, your Na also will remain constant. So, now the only thing is your final resolution is proportional to your wavelength. You put the values and you will get the final result. Let me just erase this for now. Yeah. So, you put the values in this case and you will get the final value. So, particular ratio, right. So, again putting values and get the thing that even calculator can do, but how you have reached to this particular stage, how much you understand this emission spectra, how your final resolution changes based on your different parameters and all is something very important. So, again an example based on resolution, we will quickly move to the third example. So, in the third example, in an optical lithography system, a krypton fluoride source is used with 2 beam imaging. So, one thing is krypton fluoride source is used, right. So, if you go to the previously the emission spectra, krypton fluoride wavelength is identified. It if you go lower in terms of wavelength, you will get a smaller resolution. So, that is why we have gone one step lower to krypton fluoride source. You can even take argon fluoride source or even lesser than that if possible. Now, somebody will say UV light yields wavelength of 13.5 nanometer. Why can't we directly use that? But that comes with its own pros and cons. When I talk about extreme UV lithography, that won't work on the same principle what this excimer lasers or mercury lamps works. So, optics changes, principle changes, formulas changes, and finally the entire structure or arrangement of lithography changes. However, it is possible. EUV people have fabricated several things and there are different techniques and all. So, for now we will focus on krypton fluoride source is used with 2 beam imaging. Okay. 2 beam imaging, which means there are 2 types of imaging, one is 2 beam, one is 3 beam. I will come to that. It depends on how your light or how your source illumination happens with respect to a condenser lens. If this is your condenser lens and this is your source, if there is a normal incidence, then it will be 3 beam imaging. If there is a oblique incidence, there is a 2 beam imaging. Based on that, K value will change. Normal incidence, let us say this is your condenser lens, normal incidence, you normally apply the light, then it will convert into 3 beams, it will be 3 beam imaging, K value is 0.5. When it is oblique incidence, this is your lens, this is oblique incidence, then 3 diffracted order of light, one of them will go out of range for a particular subsequent lens and only 2 beam reaches to the lens, which will make 2 beam imaging and your K is 0.25. This is process parameter known. Okay. So, 2 beam imaging, consider that numerical aperture at 1.35. Now, when you change the medium in between your mask and lenses, mask comes in between condenser lens, objective lens, when you put in between medium you change it, then your numerical aperture will change, okay, and accordingly you will get an improvement in resolution. So, we have been given krypton fluoride source which will give us wavelength, we have been given 2 beam imaging which will give us the value of K and also numerical aperture. So, what do you want for resolution? R is equal to K lambda by Na. So, required things have already been given, but let us see what further problem statement says. Compute the optimal resolution that can be obtained for the given setup. Put the values, get the put the values and get the final resolution what you can get. Next B part of the problem statement is, will the given parameters fulfill the requirement if a process require a 120 nanometer pitch. Slowly gradually we are moving towards a kind of a numerical which is like actual design based numerical. Of course, it is like an ideal case what we are considering, but still they have asked a question, if you want to make a microstructure which has a pitch of 120 nanometer with the given parameter, will you be able to get that particular thing or not. Okay. So, we will approach this solution now. As I said, first step is very simple. This is what I was explaining, this you already know, and source condenser. See here, towards the mask, this particular light is illuminated normally, right. This angle, if you see, okay, this angle of light and mask is 90 degree. Okay. So, it is normal incidence of light, normal incidence, okay, which will result in, let us say here there are 3 beams, 1, 2 and 3, all 3 is acquired by objective lens. So, then normal it is normal incidence. So, it is called 3 beam, whereas in some other strategies, if you are using oblique incidence, okay, then this would be, I will use a different color. So, it would be easy for you to understand. Okay. Let us say instead of this we will be using this imaging. So, this is oblique incidence, okay. This is for illustration I am doing. So, when it gets diffracted, some of them will go like this out of the range of your objective lens, other part will might come here, other part will come here. So, only 2 out of 3 beam will be acquired by objective lens. So, that is again will decide by your numerical aperture. Numerical aperture, as I mentioned, ability to acquire a particular portion of your length, which will give also lead to a limited fidelity of your finally acquired light on your wafer. So, these are 2 types. So, like this, if it is like this oblique incidence, okay, then it is 2 beam, okay, and for this your K value is 0.25 and for other 3 beam K value is 0.5. Which is better? Lower the K value, better it is for us, it will result in improved resolution. So, overall idea about how this optics and values and parameters and all are getting changed. So, now let us see quickly whether it will fulfill or not. So, I will just put the values as I mentioned for krypton fluoride loss light source lambda is 248 nanometer, numerical aperture is 1.35 and for 2 beam imaging your K value is 1/4 or 0.25. Okay, you put the values, you will get a number 45.92 nanometer, okay, which is the smallest half pitch which you can successfully print on your wafer. It is a half pitch. Now, what scenario has given to us? That process requires 120 nanometer of pitch. If you can get less than that, excellent. If you cannot get, right, there is a problem. So, we are able to get, and ideally if you want like 190 nanometer pitch, then your final desired pitch should be around 190, then you can do it 120 nanometer perfectly, because not all the values or parameters are ideal. So, there will be like some change or some process related aberration or optical irregularities occur during the process, and you might have some buffer or some gap. So, what I mean to say with using with that is this resolution is 42.92, which is the half pitch that you can successfully print on the wafer. So, which gives me a full pitch of 91.84. If I make it even more simple, 92 nanometer pitch, this existing experimental values or setup can give me 92 nanometer pitch. Now, how much nanometer pitch we want? That is 120 nanometer. So, 120 nanometer pitch is your desired, whereas you are able to, with this you are able to get 92 nanometer very easily. Hence, if anything greater than 92, obviously your system would be able to do that. But when I say greater than 92, that is better to keep a little bit gap. So, that is why this gap is good enough. If I say 92, 120 is almost 30% more from 92. So, this gap is adequate enough to proceed with the patterning. So, yes, a structure with 120 nanometer can be printed with the projection setup. Okay. So, a very simple small example when it comes to lithography or resolution, but the agenda was to make you people realize that how this final structures and all will be designed based on known things on lithography, okay, or lithography optics. So, now I will just quickly summarize, or wanted to give you a current picture. So, over the decades the resolution has been improved, right. If you know, Gordon Moore, the founder of Intel, has come up with an observation that every 2 years the size of your electronic components on your wafer, or like on your footprint, it gets halved. So, at every 2 years you will get a higher technological node, which is known referred to the feature size which you can print, and that has been followed since last 4 or 5 decades. Gordon Moore recently passed away, but his observations still get like follows, and now there is a research known as more than Moore. So, like how over the decades resolution or lithography related statistic, or which parameter has contributed more to get the resolution. So, we will quickly see that. So, if you see here, there is an improvement compared to 1975 to 2010, and there is an improvement based on each particular aspect. So, resolution, already you know the formula, there is a K, this is your K, this is your lambda, this is your Na, and this is your overall resolution, right. 1975 we were working with this technology or node or something which is like 2.7 micrometer. Here in 2020 we are successfully fabricated something which is on 42 nanometer. Here there is a like one more tab if I can add, or one more field, okay. So, we are currently in 2023, right, and foundries have successfully fabricated something which is 3 nanometer. So, you can compare 3 micrometer was here in 1975, by 2025 definitely we have reached 3 nanometer. So, 10 power minus 3 10 power 3 improvement, I was seeing relatively 10 power minus 10 power 3 improvement, 1000 part of micrometers we were able to successfully fabricate in a way. Which parameter has contributed more and all, this is taken from one of the, I believe, IEEE article or something on this. So, I would encourage you to see this. See, wavelength is very limited improvement, like 193 also, and whereas in EUV we are using 13.5 nanometer, but with a different physical principle. Numerical aperture, it is 8.4, 8.4 is like a biggest improvement compared to all the other parameters, and we are getting 3 nanometer, okay. So, I wanted to explain little bit on how much smaller dimensions we can get, okay. So, this is like a consider one excimer laser. I wanted to give a best case scenario. So, I will say consider argon fluoride laser. So, that you should know now what should be the wavelength 193. Use oblique illumination, which I have shown before, K value 0.25. Consider highest numerical aperture, check it whatever highest you can get. If you do not, just consider 1.35 and identify what is the smallest dimension you can get. So, this is like a homework for you, right. Check it how much you can get, and then you map that particular value to this value. Let us say this will give you around 100 nanometer, okay. So, you are based on this projection lithography, you can take it as 100 nanometer. How did you reach to 3 nanometer? What did you do that? Okay, that is what foundry have successfully fabricated resolution of 3 nanometer, how it is being done. So, that is something I would like to leave it to you, up to you, that you can explore by your own and try to identify, and this like it is not one particular approach, there are several approach combinedly works, and to this particular to achieve this particular resolution. So, like quickly if I say, these are like a different see from growth, how we have reached from 20 nanometer to 10 nanometer to 7 nanometer, right, to 5 nanometer. So, this is like different types of patterning. There is something called double patterning, triple patterning, quad patterning, self aligned double patterning, which you can see here, and there is some other patterning techniques, combination of that, EUV is here. All this thing will be used to achieve a particular resolution. So, this is like I wanted to give you an idea, of course based on your interest and all you can explore more. So, like overall gist of the session is how you can get desired final resolution, to have more and more functionality on your device. So, this is what I wanted to convey in this particular class. I believe now you will be able to relate with whatever lithography related optics and all this thing. If you have any questions or difficulties, feel free to write us on the forum and explore this concept at your own. Thank you.